Hi everyone, it's not rocket science. Or maybe...
Actually, it is.
So, we are going to do more rockets today. I'm going to show you many attempts and we are going to apply a little bit of physics, basic physics, and the second and third laws of motion by Isaac Newton. And we are going to study Matchbox rocket science. Okay, we have here three different kind of matches. The usual ones that I've used so far. These ones that are in fact a bit bigger. And the huge ones, all right? Okay, we need to measure a few quantities. First of all, we measure the length of a match, a bit more than 4 centimeters, including the head, and I would say 3.8, 3.9, 3.8 centimeter, getting rid of the head. Of these medium ones, more or less 5.5 centimeter, and the head is around 3 millimeters, maybe 4. The full length is 9.7 and the head is 7 millimeters. We now measure the mass of the matches. It's 2. Okay? And we count how many there were. 1, 2, 3, 15 and 16. Okay. The box of the medium ones is new and contains 60 matches. The whole box is 17 grams. Only the box is 7 grams. So 60 matches are 10 grams. The big ones, including the box, 55 matches are 37 grams. And only the box is 15 grams. So 55 are, okay, yeah, are 22 grams. To measure the weight.
Then we need to measure the mass of the aluminum foil.
We take a sheet which is, let's say, 50 centimeter times 28, 3 grams. Okay, perfect. A typical rocket. Let's see how big it is. Let's just forget the little piece that I get rid of to approximate everything. This is something like 6 centimeters times more or less 7. Okay. In the end, we need to compute the mass of the fuel, the head of the match. Okay. I will assume that the igniting material is equal to the mass of wood in the head of the match. So using the measurements done before, we obtain a mass for a small match of roughly 0.1 gram, or a medium match of 0.2, and a big match around 0.3, 0.4 grams. Using the ratio of length of the matches and heads and what our assumption of the igniting material's mass, we get immediately the mass of the head including the igniting material. Finally, adding the mass of the aluminum foil, we obtain the mass of the full rocket. So now we have some basic physics to study. So the distance traveled by an object in movement with a given initial velocity and constant acceleration over the time delta t is given by this first equation that you have here on top. If there is no acceleration, the velocity of this object is the distance traveled divided by the time needed to travel. If the initial velocity
is 0 and there is a constant acceleration for a period delta t, then the acceleration is given by 2 times the distance divided by the square of the time. Remember then the second law of motion by Isaac Newton. The force that is applied on an object with an acceleration A is given by its mass times the acceleration. Now, in our rockets, we have the exhaust gas that is flowing out of the rocket, pushed by a force that is given, let's say, to make the story short, by the combustion. Now things become a bit more complicated. For the third law of motion, the rocket receives a force in the opposite direction, and this force is called thrust. The rocket thrust can be expressed as the product of the mass flow rate of the exhaust gas times its exhaust velocity. Finally, the specific impulse of the rocket propellant can be computed as this exhaust gas velocity divided by the gravity constant, and this is just to make so that units are uniform and consistent. We are going to apply this to the best launches of our small Matchbox rockets. So now we need a measurement of firing time. So basically the time over which acceleration was active. This is the most difficult measurement because we are recording at 60 frames per second, so we cannot go below 1/60th of a second in time resolution. So analyzing the various recordings of I don't know how many different launches, you will find them later in this video, I came to the conclusion that this firing time is not longer than 2 frames, so basically 2/60ths of a second for the small and medium matches, and around 3 frames, so let's say 1/20th of a second for the big matches. This measurement is very rough because we would need to have a much higher frame per second recording. But I mean, this is the best we can do, and it's a strong assumption. I would call it this way, but that's the best we can do. Boom! This is first small match, very good launch, probably the best I've ever done. And as you see, it takes 4 frames to reach the 1 meter, and the firing, I would say, is 1 or 2 frames only. And this is an example with a medium match. 1, 2, and the firing is over. All right. And finally, with a big match, 1, 2, 3 frames, and then the firing is over again. So I would say this is a good compromise, not super reliable measurements, but better than nothing. Oh, now we apply some of the physics we learned. We compute the average velocity of the rockets using the time needed to travel for 1 meter, and we obtain 15, 9 more or less, and 5 meters per second. The heaviest rocket travels at the slowest. Similarly, it's more difficult to accelerate a heavy rocket, so we can compute the acceleration, assuming it's constant over this time interval called delta t firing, and we go all the way to 900 meters per square second, which corresponds to 90 g for this rocket built with a small match, and then 500 and 200 meters per square second for the other two. We can then play with Newton's laws of motion. So the second law of motion, the force equals the mass times the acceleration. We compute the force very easily with all the various numbers we have derived before. And we have a force of 0.1 Newton pushing the rocket built with the small match, and weaker forces pushing the medium and the big match. Now, ignoring the mass of the ashes that are left in the combustion chamber, we can compute the exhaust gas mass flow rate, so-called m dot. I didn't have the dot symbol here, which turns out to be more or less half a gram per second discharged from the rocket. And finally, we can derive the exhaustion gas velocity and the specific impulse. And this turns out to be between 25 and 6 seconds, depending on how we built our rockets with the small or big or medium matches. I had a lot of fun doing this. I hope you enjoy, and I'm now going to show you many other launches, also with some means for computations. If you like to do it, I'll let you this little homework. I think for now this video is long enough. Super. Cool. Okay, I hope you enjoyed this little demonstration of physics. Do your own experiments. Maybe you can make your own measurements and computations, and let me know what are your findings. For now, I say goodbye, have fun, always in full safety with Matchbox rockets. Ciao, ciao!